I'm from Ankara. I'm Ozcan Koysuren from Ankara University, Turkey. I will today talk about the preparation of boron carbide and silver ferrite heterostructure for photoreduction application of chromium-6. Let me introduce you the topic a little bit. Chromium-6, as you know, is a heavy metal and mostly found in wastewater and also soil. And there are some sources for chromium-6, like metal plating in industries or the refining, power generation, leather manufacturing, textile. These industries are the main source for chromium-6 to release into the wastewater. Chromium-6 is a heavy metal, as you know, and also it is dangerous, cancerogenic, mutagenic tendency it exhibits, and it's considered as a high priority pollutant. Then it needs to be removed from the wastewater or soil. There are several techniques like microbial reduction, membrane filtration, adsorption, chemical precipitation, and photoreduction. In our study, we have utilized the photoreduction technique to remove chromium-6 from wastewater. The mentioned techniques, apart from photoreduction, the mentioned techniques have many disadvantages like chemical consumption, additional processing, chemical sludge formation, and also high cost and high treatment cost, and byproducts also, in addition to chromium-6. What is the main advantage of photoreduction? Photoreduction techniques provides us to convert chromium-6 to chromium-3. Chromium-3 is a nutrient. It's not so dangerous as chromium-6. Unlike chromium-6, chromium-3 is less toxic. It is regarded as safe in drinking water also. The reduction of chromium-6 to chromium-3 is important also for the living beings, since it is utilized as a nutrient for the living beings in the environment. To remove, by using the photoreduction technique, we need photocatalyst. There are several photocatalysts utilized in the literature, like titanium dioxide, zirconia, copper oxide, zinc oxide, carbon graphite, carbon nitride, and tin oxide. This technique is a simple process and it requires minimal processes. This technique is devoid of sludge formation. This is also critical and also economical. It's also economical process and sustainable. As I said, we need a photocatalyst. Most of the photocatalysts illustrate limited photoreduction performance owing to several reasons, like poor chromium-6 absorption ability because of charge on the photocatalyst and also the charge of chromium-6. Mostly used photocatalysts have wide optical band gap, and the main problem is most of photocatalysts exhibit high recombination rate of the photoexcited charge carriers. This is the basic problem, especially for its pure usage of photocatalyst. We use boron carbide select as a photocatalyst boron carbide. Boron carbide is a metal-free photocatalyst and driven by visible light, since it is almost a narrow band gap. The stability and abundance of boron carbide are seen as significant advantages over traditional metal oxide photocatalysts. It can be synthesized by several techniques, like mainly it is synthesized by carbothermal reduction and also magnesiothermal reaction of boron oxide at high temperatures, around 1500 centigrade degree, really high temperatures required. There are also additional techniques like plasma-assisted chemical vapor deposition, molten salt combustion technique, and also there are also sol gel techniques. We have utilized sol gel method to synthesize boron carbide from polymer precursor. Apart from the methods mentioned, boron carbide can be synthesized in powder form using a polymer precursor. This is a simple process. Again, we need exothermic reactions, high temperatures, but relatively low temperatures compared to the previous methods. Nearly 1000 centigrade degrees is enough to convert polymer precursor to boron carbide. We used, first of all, we synthesized polyvinyl borate with the polymer precursor, and then by applying heat under argon atmosphere, we converted the polyvinyl borate to boron carbide. by using a simple process, just only the heat treatment under argon atmosphere. When we look at the boron carbide possesses crystal defects and distortions in its structure, this crystal structure, which results almost narrow optical band gap. Its advantages in terms of the ability to usage of sunlight. But the crystal defects and distortion can cause also the mid-gap energy stays between valence band and conduction bands, and this mid-gap stays can promote the recombination of photoexcite charge carriers, and we don't want this situation. To solve the problem, the high recombination of photoexcite charge carriers, we need to couple boron carbide with another semiconductor to produce heterojunction structure. In literature, boron carbide was coupled with titanium dioxide, zinc oxide, carbon nitride. In our study, we have selected silver ferrite. It's a suitable semiconductor. It is magnetic properties. It's also important. Magnetic properties also important with the help of the magnetic property of silver ferrite, we can separate the composite after chromium 6 photoreduction experiment or the process. It's easily also synthesized silver ferrite. It exhibits better properties like recyclability, reusability, eco-friendly chemical and photochemical stability also. Also, it includes silver, and silver is important for the promoting the separation of photo-induced charge carriers. Okay, what is our objective now in this study? Our main objective is to suppress the high recombination rate of photo-induced charge carriers on boron carbide. For this purpose, we have coupled boron carbide with a magnetic semiconductor. This is silver ferrite. We utilized the differences and in conduction band and valence band energy. There is the difference, as you can see here in the figure. There is a difference in the band energies. Because of this band energy differences, electron can transfer from the conduction band of silver ferrite to boron carbide, and also the photo-induced hole can transfer from boron carbide's valence band to the silver ferrite's valence band. So we can separate effectively photo-induced charge carriers on boron carbide. Let me talk about the experimental study. First of all, we have synthesized boron carbide by using, first of all, we synthesized polyvinyl borate. This is the polymer precursor, by using polyvinyl alcohol and boric acid, just by using the simple sol gel techniques. Then we applied high temperature under argon atmosphere to convert the polyvinyl borate to boron carbide. And then we dried, after necessary purification and cleaning steps, we obtained the boron carbide in powder form. After synthesis of boron carbide, then we synthesized the silver ferrite in the presence of boron carbide to prepare the composite structure. For this purpose, we used silver nitride and iron nitride. These are the precursors of silver ferrite. Again, simple sol gel techniques are utilized, especially here the auto-combustion reactions results the formation of silver ferrite in the presence of boron carbide. Then we dried after necessary purification, then we dried the composite sample and then applied the calcination, high temperature treatment to improve the crystallinity in the structure. Several characterization tests are performed, like FTIR, XRD diffraction technique, SEM microscopy, nitrogen absorption distortion studies, the potential measurement, UV absorption spectroscopy, photoluminescence spectrum, and saturation magnetization test. And the critical test is here, the chromium 6 photoreduction experiment. For this purpose, a homemade setup is utilized. We prepared the chromium 6 solution. We add our photocatalyst into a sample, and after necessary absorption equilibrium step, we utilized a diphenyl carbazide DPC technique to visualize the reduction in chromium 6 concentration. Here you can see if the IR spectrum of A belongs to boron carbide. As you can see here, there are characteristic peaks of boron carbide. And when we look at spectrum B, you can see the characteristic peak of iron oxide. This peak shows us that we synthesized boron carbide and silver ferrite successfully alone. And also peak C and peak D belongs to composite structure. We can see the peaks of both boron carbide and silver ferrite on the composite spectrum of composite sample. This just to prove the chemical structure of the composite and the pure samples. Then we have performed XRD measurement to visualize the crystallinity. It is really important in terms of particular activity. High crystallinity is really important. When we look at the graph, diffractogram A belongs to boron carbide. There are several peaks belonging to characteristic rhombohedral structure, crystal structure of boron carbide, as you can see here. And when we look at the diffractogram B, we can see the characteristic peak of silver ferrite cubic crystal structure, especially. C and D belongs to the composite structure. We can see all of the peaks belonging to boron carbide and also silver ferrite. As you can see here, especially for composite samples, there are high crystallinity. It's only really, as I said, important in terms of physical activity, especially. Here you will see the photoluminescence spectrum. Why we have performed this analysis? Photoluminescence spectrum shows us we utilize this graph to comment on the recombination rate for excited charge carriers. If there is a decrease in the peak intensity, then we can say that there is a decrease in the recombination rate. The curve A belongs to boron carbide and B belongs to silver ferrite, and C and D belong to composite samples. As you can see here, compared to pure samples A and B, there is a decrease in the peak intensity, peak maxima, which shows that we decreased the recombination rate compared to pure sample by coupling these two samples. This is also our aim in this study. Here you will see the nitrogen absorption desorption isotherms. We have done this experiment to see whether there is a surface area effect on the chromium-6 removal. We can see on table this one belongs to the boron carbide and this one belongs to the silver ferrite and this belongs to the composite sample. There is a decrease in the effective surface area compared to pure boron carbide and also a decrease in average pore size and pore volume, which means that there is a decrease in effective surface area. Then we can say that the reason for the enhancement in the chromium-6 photoreduction rate is not the surface area enhancement. There is a decrease. Then the only reason can be the coupling effect and hence the suppression in the recombination of excited charge carriers. Here you will see the SEM images. A belongs to boron carbide. You can see the crystal structures, sizing between 1 to 10 micrometer, and B belongs to the crystal structures of silver ferrite. You can see these structures, particles ranging from 1 to 2 or 3 micrometers. When we look at C and D, this belongs to composite structures, including different amounts of silver ferrite and boron carbide. There is a homogeneous distribution of particles in each other. This is also important since a stable contact between silver ferrite and boron carbide is really important to separate the charge carriers from valence band and from conduction bands. Now you will see the UV visible absorption spectrum of pure samples here on the left and on the composite sample. Especially the UV visible spectrum of composite sample exhibit us they can absorb, the composite sample absorb the incoming light starting from 500 nanometer until the UV range 200 nanometer. This especially UV range and also the it includes all certain parts of visible light range. This is especially critical for the sunlight application. Here, this is the critical experiment for us, chromium-6 photoreduction results. On the left, you will see chromium photoreduction rates for pure samples. A belongs to boron carbide, and the other one belongs to the magnetic semiconductor silver ferrite. Pure silver ferrite results really low photoreduction rate of chromium-6, but when we look at the boron carbide, it exhibits almost 60% of photoreduction of chromium-6 at the end of 132 hours, within 2 hours of UV visible light irradiation. When we look at the composite samples, there is really a significant increase in the photoreduction rate, especially the sample. If this one belongs to the composite sample, including with the weight ratio of 10⁴ of boron carbide to silver ferrite, it exhibits nearly 97% of photoreduction rate at the end of 2 hours. This is a really good number, and there is a significant increase. Now you will see the effect of certain solution conditions and ingredient and pollutants or the solution medium conditions on the chromium-6 photoreduction rate. On the left, you will see the scavenger effect. We have done this experiment to investigate or to reveal the photoreduction mechanism. In the presence of electron scavenger, there is a decrease, there's really a big difference in the photoreduction rate, which means that photo-induced electron is the active species in the chromium-6 photoreduction experiments. When we look at right, you will see photoreduction experiment in the presence of simulated distilled water, a simulated water environment, and the other one, this one, II belongs to the photoreduction experiment conditions. By water environment, there is a decrease in the photoreduction rate. This might be due to some ingredients and pollutants present in the real wastewater. Now you will see the effect of solution pH, the initial solution pH on the chromium-6 photoreduction experiment. See the solution medium rate and the basic solutions decrease the photoreduction rate. This might be due to the surface charge. When we look at the potential graph, you will see when the solution medium is acidic, the surface charge of particles converted to positive, the surface becomes positive. If the solution is basic, then if pH is high, then the surface becomes negative. If surface is positive, we expect interaction between the negative chromium ion and the positive surface charges, and this increases the surface absorption and also, and additionally, the photoreduction rate. Now you will see on the left, you will see the effect of initial solution concentration. We have changed the chromium-6 initial solution concentration, 10 milligram liter to 15 and 20, 25 and 30 milligram per liter. 10, 15 and 20 milligram per liter did not affect too much the photoreduction rate, but if increase the chromium-6 initial solution concentration up to 25 and 30 milligram per liter, there is a slight decrease. This might be due to the blockage of incoming light. When we look at the graph on the right, you will see the reusability test results of photoreduction experiment. After 4th cycle of experiment, there is a nearly 20% decrease in the photoreduction rate of chromium-6. This might be the blockage of effective surface area, partially blockage of effective surface area after 4th cycle. Just at each step, just a simple cleaning steps are utilized for each step. Now you will see the magnetic hysteresis loops of silver ferrite on the left, and the right, and at the right, these two belongs to the magnetic hysteresis loops of composite samples. As we expect, because silver ferrite is has magnetic property, we expect high magnetization value. Pure sample exhibit really high magnetization value. As we expect, there is a decrease in the composite sample because there is silver ferrite. It has no magnetic property feature, but still it conserves its magnetic property at a certain amount, and this value is also enough to separate the composite samples after chromium-6 photoreduction experiment easily. This is really important, since these particles are in nanosize, and it's not easy to separate this particle, and which results the loss of photocatalyst during the process. As a conclusion, the highest removal rate was obtained with the composite sample, including boron carbide ferrite with a ratio of 10:4. Coupling boron carbide and silver ferrite enhanced the chromium-6 photoreduction efficiency due to the suppression of the recombinational photoexcited charge carriers, the real wastewater environment. The initial solution concentration and the initial solution pH had pronounced effect on the chromium-6 photoreduction efficiency. Why will the chromium-6 removal rate increase under acidic conditions at low pH? The removal value significantly decrease under basic conditions. Thank you for your attention.